I think it's time. I will just quickly remind that we'll have a Zoom photo right after Eleonore's talk, and also a photo just outside immediately after that. So we'll continue with Eleonore Faber's talk on matrix factors.
Today I want to finish what we started yesterday, namely comparing maximal Cohen-Macaulay modules over a hypersurface with maximal Cohen-Macaulay modules over the branch cover, and then also go finally a little bit beyond hypersurfaces and see what maximal Cohen-Macaulay modules are more generally over Gorenstein. And so I just quickly recalled what I did yesterday. So we have this R is always the hypersurface ring, and then the double branch cover is just add a new variable squared. And then we defined those two functors, sharp and flat, that send a module from R to a module on the double branch cover, and the other way around as well. And both functors preserve maximal Cohen-Macaulay. And so now the next question is, well, these are the maximal Cohen-Macaulay modules, but what about the matrix factorization? So what do these functors do to matrix factorization? And so I'll describe both of them quickly. So the first one is if we have a maximal Cohen-Macaulay module over R, then we have seen, well, we can find the matrix factorization. So we know that M is the co-kernel of the map that I called A, but now I call it phi, because essentially in the literature it's called phi. So we can also find the second matrix, so phi and psi. So these are the matrices that were formerly called A and B, so like that. And we get a matrix factorization that looks like, I just that I don't have to write as n all the time, so this is just 3 S modules of the same rank. And so here we have F5 and phi. Matrix factorization. And then the resolution. So then we know, so M is a module over R. So it is also a module over S adjoint Z. So the resolution of M over Z is given by the following. So 0 M, and then I'll just denote with a twiddle the lifts of F and G to S Z. F twiddle. Here we have that correctly. And so what do we have as maps here? So phi and Z times the identity. Then here psi minus Z1, Z1, and phi. So yeah, you have to show that this is actually a resolution which is done in the book by Yoshino, for example. And so what is important here is that, well, in order to get the M sharp, we need to get the syzygy. So the syzygy is down here. So this here is the co-kernel of this matrix here is the M sharp that we are looking for. And so it follows that the matrix factorization of M sharp is given by the two matrices, psi minus Z1, then Z1 phi. Here we have phi 1 minus Z1. So if you multiply those two together, you should get the Z squared plus X. And so now we have one of the matrix factorizations we're interested in. But so as a corollary, we can also compute, well, what happens if I sharp again? So if I do double sharp, so what is sharp sharp? So this is just by definition the syzygy over I sharp of M sharp. And so you just calculate that, and so using this matrix factorizations here, and that is just equal to M sharp. So this means we are like, it's idempotent, so we cannot sharp infinitely many times, always the same one. And also we can calculate what happens when we have M sharp B, because we can sharp, and then B just means we kill the Z, and this, then you see immediately what you get. So if you set this just Z equals 0, then you just have the direct sum of those two guys. And well, this is the corresponding module is the co-kernel of the maps. So we get M plus the syzygy of M. So this is what happens if we do both functors. And then the other direction, so now we know sharp in terms of matrix factorizations. And so now the flat, so for the flat, here we have what I wrote down here, namely that R sharp is a free S module of rank 2. And so this means that the N is also free as an S module. And so N is a free S module. And so the set, this is an element that's not contained in S. And so but we can multiply N by Z and express that as an S module. So what is also said. So phi is the matrix over S representing the multiplication by Z. And so this gives us a matrix. And then this is also something I won't show, but it's a proposition, namely the matrix factorization of N flat is given by phi and minus phi. So this is now multiplication by Z. And then if we go up again, so what is the matrix factorization of N over S over the double branch cover, then you see the following. So if we consider that 1 plus or minus phi as a matrix over S mod Z, then so this phi doesn't have entries that contain any Z, and so I can just look at this as a matrix of entries in S Z. So then we have that N is given as co-kernel minus phi, so as the matrix factorization Okay, so this is a direct calculation. And again, corollary, now we can compute the other side, the other direction. So we have M sharp flat, and so now N flat sharp. So N flat sharp is equal. Oops, I should mention something here, because this is precisely for the characteristic not equal to 2 is needed. Because we need to do row and column operations, but I don't notice that here. So if we can invert 2 in S, then we have that N sharp is precisely N plus the syzygy R sharp. So for maximal Cohen-Macaulay module, the branch cover. And also this shows us how to get from maximal Cohen-Macaulay modules over the double branch cover up, down, and also how we get up. And in particular, in this process, we are not like getting any new modules. We're just only getting the syzygy, either by going up or by going down. And so if you stick all of this together, we arrive at Flurry's theorem. It says, so first of all, if the double branch cover R sharp has finitely many, or also do the same argument countable classes Macaulay modules, then the R, so meaning if our double branch cover is a finite Cohen-Macaulay type or countable Cohen-Macaulay type, then also R itself is of countable Cohen-Macaulay type, and the other direction is 2 if 2 so if it's vertical, then other direction. And again, essentially, well, the proof, actually, I put it in the notes, at least one direction. So maybe I say, so you assume that, for example, R sharp is a finite Cohen-Macaulay type, and you can decompose it into, then you can decompose any maximal Cohen-Macaulay module into the same, into the generating modules, and then you just calculate sharp and flat, and you see it's still finite. So I refer to the notes. And yeah, the one thing you should probably note is that we always have, so M sharp flat is M plus the syzygy over R of M, and also if we have M flat sharp, is just N plus syzygy R sharp. And so they always split, but it's unclear, like if you go down in splits and you go up, or if you go down, nothing happens and then it splits. So both can happen. Okay, so now we have the theorem. Let's give you a nice example for this. Namely, what can you show with this? The finite, the characterizations of hypersurfaces of finite Cohen-Macaulay type. And so example in the high correspondence. So well, this gives us all the finite Cohen-Macaulay type rings of dimension 1 and 2. So first of all, well, it's a fact, or it's a calculation which was proven by Royal in 1985, quite a while ago, is that the ADE curves, so ADE curves, so yesterday I made this like slightly incomplete list of AD and E hypersurfaces. So these are the curves that are of the form C, X, Y, below F, where F is of one of these either AN, EN, E6, E7, or E8. And so Brown and Turner proved that ADE curves are of finite polytype. And well, now what happens if we do this double cover? So we can just add a square to our F here. So the R sharp in this case is then just C X, Y, Z. And then here we have Z squared plus F. And so, well, what is this? This is an ADE surface singularity. And well, so from Knurrer, we already know this does have finite Cohen-Macaulay type. But another way to see that is that this R sharp can be seen also as a invariant ring under a finite proof, namely G in S2C. And so for each ADE surface, we have one finite subgroup of SL2. So for the ANs, we have the cyclic subgroups. For the DNs, the dihedral subgroups. And E6, E7, E8 are the symmetries of the tetrahedron octahedron icosahedron. And well, then how can you, so in order to get the matrix factorizations over the surface singularities, well, you can just calculate matrix factorizations over the curves and then add the Z, or as originally done by Gonzalez, Springer, and Berthier, we directly computed this multiplication by Z and got the matrix factorization. So okay. Matrix for by looking at this multiplication by Z. And in this case, it's quite nice because this multiplication by Z in this case has to do with the reflection groups. But well, what you get in total, which is the Mackay correspondence, is that we get that the matrix factorizations, so I think I denoted them by S, that ADE surface singularity corresponds 1-to-1 to the maximal Cohen-Macaulay modulus for French cover, and this corresponds 1-to-1 to the irreducible representations of this group G. And yeah, you can do that all a bit more generally. And also, you can also interpret these ADE curve singularities as or the maximal Cohen-Macaulay modules over the ADE curve singularities correspond to irreducible representation of the corresponding reflection group, in which G sets of order 2. So that's another way to see that. So this about the Mackay correspondence. But one concrete example, because yesterday I was like asked for examples of this and of finite Cohen-Macaulay type. So let's do one of the curves, surfaces. See how this relates to the curves. And so yeah, in particular, you see that the number of matrix factorizations for maximal Cohen-Macaulay module is precisely the number of irreducible representations of this group G. So concrete example. So let's do the D5 surface because interesting splitting is happening. So the equation here is x squared y plus y to the fourth plus z squared. So this here first part, and this be the f, and this is the z square. So our sharp is that squared, and our y f. And then, well, how can we? So I'm not writing down the matrix factorizations. I just write down the else on the right in quiver. So we have 6 indecomposable modules. Yeah, so maybe I should say here, why do I get the else on the right in quiver? Why do I know this? Because we also know that in this case, G is precisely, and it is the same as the AR are sharp. And so the Mackay quiver of D5 is always to ADE always corresponds to a corresponding extended Dinkin diagram. So this means it's an extended D5. So we have 6 indecomposable modules or irreducible representations. And they look as follows. So here we have M1. Sharp. And 5. So these are the 6 modules. And there you can find the actual matrices either in the Yoshino book or in the Leuchter-Wiegand book. And then if you go down to R, so the R quiver of R, so well, what happens? So either if I go down, the module stays indecomposable or it splits. And if it stays indecomposable, it could happen that, for example, if you restrict 2 representations, they give you the same representation, so the modules will become isomorphic. And so precisely that happens here. So maybe I can just finally some colors. So these two will become isomorphic, and all the other ones will split. So this one splits, this one splits, and this one splits, and yeah, R obviously R stays always R. Nothing's happening here. So okay, so now let's see if I can draw this thing. So here we have N4 flat, N5 flat. Maps are here. I've done it like David painted. Let's see if that works. So this is here the N1 flat, second N1 flat. And here, created here, and our so this is what happens to the Macaulay quiver. And you can actually check that if you take the reflection group, then this is actually the Macaulay quiver of the reflection group. Modulo the trivial representation. Okay, so far so good. Maybe that's good question. Good time to ask any questions. Okay. Also, then I can finally come to the periodicity. So this is now, so we can add one square. So why don't we add more squares? And this is the double French cover. So this is, if you look at our chart, and so this is two variables, and then well, we can again do the same game, like what is happening to the module. So from n to n sharp to sharp. Then you see, oh, this always decomposes, but then we can do a little trick. So coordinate transformation is that u equals z plus I w, and v equals z minus IW. So this whole thing we actually see that this becomes our short chart becomes V below F plus UV. And then if you have a matrix factorization, so if M, I just write a co-kernel by psi, meaning it's just phi, but psi is the map in the matrix factorization. So if this MCM, then we can find the double X. This is given kernel phi times V1 U phi and 1 phi. So this gives you then the matrix factorization, and we lift M to the double branch cover, and then using this one can actually prove Earth's periodicity result. that in fact, if we go, so if we skip one dimension, then really nothing happens. So functor goes to x gives us an equivalence of stable categories in the MCM are is equivalent MCM over the double branch cover. And so, well, this tells us that so these are precisely the same modules, and the only thing that changes from the dimension is, so this is just on the stable modules. Oops. The only thing that changes in the AR quiver is that actually the number of arrows into R and from R always doubles with each dimension. But that's all that happens, but the stable categories are equivalent. And so, yeah, this shows one direction of the finite type theorem, namely, if we have a ADE hypersurface, then in this example we have seen you can show that the curves are a finite Cohen-Macaulay type. You can also separately show that the surfaces are a finite Cohen-Macaulay type, and so then with this functor you can just go to any dimension and you see any simple hypersurface singularity is a finite Cohen-Macaulay type, and so it follows that all hypersurface singularities are of finite M type. And then, well, the other direction is if I have a hypersurface of finite Cohen-Macaulay type to show that it's actually an ADE hypersurface. So this is done in Buchholz-Schreier. So the hypersurface finite M type ADE. And in fact, they are showing even more. They are also classifying the hypersurface of a countable Cohen-Macaulay type. So also hypersurfaces of countable MCM type. These are just given by A, so there are limits of the ADE hypersurfaces, so it's A infinity, which is y mod x squared, and C infinity, with C squared y, and the determinal the matrix factorization. Okay. So this was the finite Cohen-Macaulay type for hypersurfaces. So now, yeah, as I said yesterday, for general Cohen-Macaulay rings, this question is open. Like, what are the Cohen-Macaulay rings of finite Cohen-Macaulay type? So this. There are some candidates for it, and there is like the conjecture that these are the only candidates. But apart from this, I don't really know. So, well, we've seen now finite Cohen-Macaulay type, and so now what was supposed to be the third lecture, but it's now only the end of the third lecture, is like going a little bit beyond the hypersurface case. So the hypersurface case, we always have matrix factorizations and correspond to maximal Cohen-Macaulay modules. But what happens to maximal Cohen-Macaulay modules over more general singularities. And this is what's singularity categories. So I should say that this is the theorem here, namely Buchwald's Orlov. So, well, they are sometimes it's a theorem of Buchwald and Orlov, but it's essentially Buchwald's just the non-graded version and Orlov's just the graded version, and some additional things. But so most of what I will be saying here, you can find in this famous unpublished manuscript of Buchwald, which actually should make a bit of advertisement, which actually hopefully will be published soon. Namely, it's planned to be published as an AMS memoir and was edited by do not forget anybody, Akramov. Great. And so they added some appendices, in particular in relation to Orlov's theorem. And so what is this about? So the whole thing is about more generally what is MCM A, where A is now not a hypersurface ring, but well, can first ask, well, any suitable ring, then you will find, oh, it's working best for Gorenstein rings. And it doesn't actually matter if the Gorenstein ring is commutative or non-commutative. So we will now switch to Iwanaga Gorenstein rings and see what that category is. All right. So maybe I should say at least a little bit about Iwanaga Gorenstein rings and Cohen-Macaulay modules. So A is Noetherian, so now not necessarily commutative, but I always assume it's Noetherian on both sides. And I'm not really using any sides of modules, but if in doubt, I'll consider right A modules. And so A is called Iwanaga Gorenstein. I'll just abbreviate that with IG. If its injective dimension on both sides is finite, so right injective dimension and the left injective dimension. So one can actually show if both of these injective dimensions are finite, then they must be equal and equal to the full dimension of the ring. So this is the ungraded case. Then you can also say something, because I guess we need that later. So in the graded case, we have that A is positive. I'll always assume it's positively graded. And also a slightly technical annoying condition is that we need that the zeroth part is always a field. And then, well, what does Iwanaga Gorenstein mean? So this means that if we take graded X into the right category, then A is just isomorphic to K minus the injective dimension of A. And then we have a shift. So this here is the shift in the derived category, and this A is the reshift. So this A here is called the Gorenstein parameter. And okay, so now
you made a remark about the first point. If these things are finite, they're equal.
Yeah.
And equal to the Gorenstein dimension of the ring. But that's if A is commutative, right? And A is not commutative, there's no statement.
You might be right. I think but I think that statement is true in general.
Well, I just don't know what the ring is. If A is finite over a ring, then that ring can be Gorenstein, but these dimensions don't have to be the full dimension of that ring.
Okay.
I think that's a good case.
Yeah, so I don't think I'll ever need that they're actually equal to the ring. So I don't need that the injective dimension is equal to the full dimension of A. So yes, so you're most probably right that
they're equal to each other. I think
they are equal
to the full
each other.
dimension
That
of A
is
if that is defined.
Yeah.
Yeah.
That is the only thing. So I can actually, this is all well defined here. That's the important part. So now that well, 2 minutes left or something, I can at least define what the maximal Cohen-Macaulay modules are over this ring. So if you have a commutative ring, then I gave you the definition of maximal Cohen-Macaulay modules as this like maximal depth module or this condition with the x. And indeed, this x condition over a commutative ring can be phrased slightly differently. And you can just take this as the definition, as you've done in Wagner's manuscript. Namely, if we have A even a Gorenstein and M finally generated A module, then M is MCM or A if definition if x I of M A is 0 for all I then 0. And so this is just a generalization of the commutative one. But well, lately there is like more work on this, and so this is actually this MCM condition has been studied in the various different names, namely so sometimes this is called totally reflexive, especially in the commutative algebra literature. So this condition here, this is totally reflexive. Or then there's a theory of Gorenstein projective modules, modules of some Gorenstein dimension. And so by Ausländer and Bridger, they gave some definitions for what is called Gorenstein projective. And so this can be defined over not only Gorenstein rings, but in general, Cohen-Macaulay rings. No, you don't even Cohen-Macaulay, you just need the theorem on both sides. And you can define Gorenstein projective definition, which I'm not giving. But in the case when A is Ivanara-Gorenstein. This is precisely Gorenstein projective. So maximal Cohen-Macaulay is precisely Gorenstein. Okay, I guess I should stop before I do the covalences.
Let's thank Eleonore. Any questions or comments? From Zoom, I don't see anybody. If that's not the case, let's thank Eleonore again.